So like I said, we've been talking this whole chapter about how to find derivatives. Okay, that's what we've been talking about. Today we're going to talk about not how to find derivatives, but does something have a derivative? Does it even have a derivative? Okay? So, three conditions, three things that we need to know. So if all of these are a yes, or sorry, if it passes all three of these conditions, it has a derivative. Okay? So first of all, it must be continuous. Okay? So it has to be continuous. So no jump discontinuity, no asymptotes, vertical asymptotes, no, what was the other one? Holes, right? If it has any of those three guys, doesn't have a derivative at that point. I can't find a derivative if I got a hole. So if I have a function and it's got a hole at 2, I'm not going to be able to find the derivative at 2 because it's got a hole there. Okay? I can find the derivative anywhere before 2 and after 2, but not at 2. Okay? So all of those, we're going to talk about those continuity rules from last chapter, but all of those continuity rules have to apply. That's the first thing. Second thing, no sharp turns. No sharp turns. I'm going to show you what a sharp turn looks like. And no vertical tangents. Vertical tangents are tangent lines that go straight up and down like that. Okay? So like if, for this guy here, if I was trying to find the tangent of anything before the hole, it would look kind of like that, right? That's the vertical. That would be it would be a positive tangent line, but it wouldn't be vertical. So anything vertical like that, can't have that. If it's continuous and it has no sharp turns and no vertical tangents, then it does have a tangent. Okay? So number one, we've talked about before. So what is 2 and 3? What are sharp turns? Sharp turns look like g of x down here. Look at g of x down here. What happens when x is 0? What does it make? Kind of like a corner, right? Corner, like the corner of your desk, right? At 0, there is no derivative because that's a sharp turn, right? You're decreasing, 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 and then all of a sudden you change to increasing, right? There's no slow gradual. If it was like this, that's okay because there's a slow gradual change. But this guy here, there's no slow gradual change. It just changes at 0, decides to go the other direction. It's a sharp turn. So at 0, everywhere before, so I don't want to make this guy seem like it doesn't have a derivative. It has a derivative all there and all there. But at 0, it doesn't have a derivative because it's a sharp turn, right? So the way I think about it is, what's the slope of the tangent line going in? It's negative, right? And then at 0, it changes. What is the slope of the tangent line coming out? Positive, something different, right? So that's why I kind of put this guy here. Means coming from the left, coming from the right. So coming from the left, the derivative has to be the same as coming from the right. If it's not, then it's a sharp turn. It's what we considered a sharp corner or a sharp turn or a corner, those things like that. So that's an example of number 2. Okay? The other one is no vertical tangents. That's called a cusp point, C-U-S-P, cusp point. What does that look like? It kind of looks the same, but a little bit different. That's an example of a cusp point. It's still got a kind of a corner to it, kind of an edge to it, right? The reason it doesn't have a derivative there is because everywhere before that dot, the derivative is negative, going downhill. Everywhere after that, it's increasing. But there, if I was to actually find the line tangent, it would look like that. And that's a vertical tangent line. Okay, if I wanted to find the tangent line to the dot there, let me make a dot. It would be vertical. So this one has that issue. Okay, so we don't want anything that has a cusp point, which is kind of like that, or a corner, a hard corner. Okay, so those are the three conditions.
So f of x would meet all the conditions except for the third one, so it's not a sharp turn?
So f of x, yeah. So f of x is continuous, right? It doesn't have a sharp turn. It's kind of, see that guy right there? See, cusp points are kind of corners, but they're rounded. They're kind of like rounded corners, whereas corners are just corners, right? So yeah, so f of x might fail 2 and 3. G of x only fails number 3, yeah. So yeah, that's how I think about it. I think about a cusp point as a rounded corner, right? It's not coming in, like these are straight lines for g of x, so yeah, that's kind of how I think about it. Hey, what's going on? Okay. So yeah, that's what they look like visually. Problem is, if you kind of flip through your our notes, there's not a lot of pictures there. There's not a lot of pictures. So it's easy to spot when you got something visual, but there's not a lot of pictures there. So we're going to have to figure out a way. How do we know if it's a corner, hard corner? How do I know if it's a sharp turn? How do I know if it's a cusp point without the nice pictures? That's what this lesson is. Okay? Okay, so first thing we got to do is remind ourselves about continuity, because continuity we haven't talked about since last chapter. Continuity was the last thing of last chapter. That was a while ago. Okay? So let's go over the rules for continuity. How do we know something is continuous? Well, limits. We talked about limits, right? The limit as x approaches some number from the left, let's call it f of x, has to equal the limit as x approaches the same number from the right. If those are both correct, then the limit as x approaches the same number from both sides has to be the same. And then the last thing is the answer at that number has to be the same. Has to be the same. That's what we did last chapter. This chapter, we're doing everything the same except replace limit with derivative. Replace limit with derivative. Take away the limit, put a derivative. It's the same rule, right? So you have these guys up here. That's essentially what that says. The derivative coming from the left has to be equal to the derivative coming from the right. That's what we're going to check. We're not checking limits with continuity or with a differentiability. We're checking derivatives. If we're checking continuity, then we use limits. Okay? So this guy right there is pretty much, and then I should probably put the derivative at that point. That's what we're going to check. So today we're checking derivatives. Unless it says continuity, we're using derivatives. Okay? All right, so let's look at example. Oh, so here, I put this on here, but it's kind of confusing. If something is differentiable, then it has to be continuous. So if you know it's differentiable, then it has to be continuous. But if something is continuous, it's not necessarily differentiable, so you have to check it. If something is not continuous, then it can't be differential. Okay? So if it's like, if it's this, then that, and it's that, then this, but not necessarily, so that's how I look at it. So if you check differentiability at a point, and you're like, yeah, it's differentiable, then it also has to be continuous. You don't even have to check continuity. But if you start with continuity, and you figure, hey, it's continuous, you still got to check differentiability. Unless it's not continuous, then it can't be differentiable. Okay, if it helps. Okay. All right, so let's look at example number 1. So differentiability and continuity go together, hand in hand. When they ask for one, more than likely they're going to ask for the other. Okay. So we have a function. We have to write whether is it continuous, differentiable, or neither, anywhere. Anywhere. Where's the only place that I would check for this guy to see? At 14, right? We did this last chapter, right? The only place I checked was 14 because that's where it changes. That's where I could have a hole. That's where I could have a jump discontinuity. That's where I could have an asymptote, right? At 14. Anywhere before, it's quadratic. Anywhere after, it's linear. Okay, so the only place I'm going to check is 14. So which one do I start with? It doesn't matter. But let's look at this table here. We want to try to limit the amount of work we do. Judging from that table, which one should I check first? Should I check differentiability or should I check continuity first? So if I check continuity at 14 and it's continuous, do I then have to check differentiability? Mm-hmm. If I check continuity and it's not continuous, do I have to check differentiability? No. If I check differentiability, do I have to check continuity? No. So it doesn't matter which one you start with. Most people start with continuity just because we've done that before. So we'll start with continuity. That's how you kind of use that table. Okay, so we're going to try, is it continuous? So this is at x equals 14, right? Because 14 is the only place we're going to check because that's where it changes from quadratic to linear. Okay. So I'm going to put a question mark here because we don't know if it's continuous yet. All right, so let's set up the definition. The definition of continuity says the limit as x approaches 14 from the left for f of x has to be equal to the limit as x approaches 14 from the right for f of x. And then it also has to be equal to f of 14. If all of those numbers are the same, it's continuous. If it's not the same, it's not continuous. So now what I got to do is I have to figure out what each of these guys is. Okay, so again, this part is review from last chapter.
Do you replace it by the derivative or no?
No, that's when we're checking differentiability. Yeah, we're not there yet. We will definitely do that, but not yet. Yeah. Okay. All right, so if I want to check this guy, what do I got to do? Use the first equation because it's less than 14, right? So I'm going to plug in 14 everywhere there's an x on the first equation. 14 squared plus 7 times 14 minus 20. So we can't use a calculator. We cannot use a calculator, so we got to kind of do some mental math here. 14 times 14 is 196, I believe.
Yeah.
Plus 14 times 7, 98? 98? Yeah, sounds right. Minus 20. So 196 plus 98 is 294. Minus 20. 274. So the limit from the left for f of x at 14 is 274. Now from the right is the positive greater than side. So let's use the bottom one. So 20 times 14 minus 6. 20 times 14, 2 times 14 is 28, so just add a 0, so it's 280 minus 6, 274. So far, good, good. How do we find f of 14?
Use the first one.
Use the first one again, right? And we already did it, so we don't have to do it again. We already got an answer. It was 274. Okay, so 274 looks like all the way across.
So it is continuous?
So it is continuous. We know it's continuous at 14. Do I have to check differentiability?
Yep.
Yes, I still have to. Okay.
Can we just put the derivative in terms?
So yeah, so now I'm going to do the same thing except replace limit with derivative. So the first thing in is I need f prime. I need f prime. That's the first thing, right? How am I going to find f prime of this guy?
Use the first equation?
Use both of them. Yeah, it's just, this looks harder than it is. Because when I say find the derivative of this guy, everyone kind of pauses and stops. It's the same thing. You find the derivative of the top, you find the derivative of the bottom. It's still going to be x is less than or equal to 14, and x is greater than 14. So the derivative of the top would be 2x plus 7, right? The derivative of the bottom would just be 20. And it's still x is greater than or equal to 14, x is greater than 14. That part has not changed. Okay. So again, now I don't care about the original. I'm testing the derivative. So let's go back. I'm testing this guy right here. This guy will tell me, I already know it's continuous, so I don't need to check number 1. I need sharp turns and cusp points. That's what I need to. How do I figure that out? Right here. So that's the guy, that's the definition that I'm going to use. F prime of C, so C in our case is 14. Okay, so let's see. So f prime of 14, oops, no. F prime, wait, yeah, that's right. From the left, f prime of 14 from the right, f prime of 14. There's no limits. Why is there no limits? Because it's not a limit. It's the derivative. Okay. So now I got to figure out how to answer these. The derivative at 14 from the left side.
35?
How'd you get that?
Plug in 14.
Plug in 14 to the first one, right? Plug in 14 to the top one because it's less than. 2 times 14 plus 7. 28 plus 7, 35. Okay, derivative at 14 from the right. Can't plug it into the bottom anywhere, right? I'm not able to plug it in. The answer is always going to be 20. What about f prime of 14? Which one would I plug it in just to get f prime of 14? Top or bottom?
The top.
Top, right? The top, and we got 35. So these guys are not equal. They're not equal. I should probably write, let me write this. differentiable at x equals 14. Okay. So now let's write our findings. So is it continuous, differentiable, neither, both?
Continuous.
It's continuous at 14, but not differentiable. That means there's some sort of issue going on. We know it's continuous, so it can't be number one. That means there either has to be a sharp turn at 14 or a cusp point at 14. Some issue like that. It's not going to be a discontinuity because we showed it's continuous. Okay, we don't have to answer why. All we have to do, it didn't say why, it just says we have to. So f of x is continuous everywhere, but not differentiable at x equals 14. It's continuous everywhere, but it's not differentiable at x equals 14. Okay.
But would we ever have to figure out if it's a cusp point or a sharp turn?
It's a great question. I've never seen that question. Yeah, I've never seen the question where they ask you like specifics. Is it a sharp turn or a cusp point? Yeah, so it's not a question I'd worry about. Yeah, that's a great question, but I've never seen them have to different. The main thing is it differentiable? Okay. All right, so now what I want you to do is try number 2. Try number 2 on your own. Is it differentiable? Is it continuous, both, or neither? All right, so -2 appears to be the only place where we would be concerned about differentiability or continuity. Okay, so I'm going to check continuity first. So -2 from the left, so that's going to be the top. So I'm going to plug in -2 to f of x, the top part. So I get 4 minus 22 plus 24, 6. And then I'm going to plug in -2 to the bottom. I get 7, -2 plus 20, -14 plus 20, 6, which is also equal to 6. Continuous. Differentiability, I got to find a derivative first. So I got a derivative of the top, derivative of the bottom. Same thing, plug in -2. Plug it into the top, I get 2 times -2 plus 11. So -4 plus 11, that's +7. To the bottom, it's always going to be +7. So they're all +7. So this one is differentiable and continuous. So we would say f of x is both continuous and differentiable everywhere, or from -infinity to +infinity, something like that. Done. Okay. So once you've done your continuity checks, differentiability is not hard because it's the same thing, just with the derivative. Okay. So this probably makes a little more sense to you than continuity did when we first did it, because you've done it. You've done continuity. Okay? All right, so now let's go to the next page. Okay, so here, determine the values of a and b, which would result in f of x being differentiable at -2. So they tell us it has to be differentiable at -2. Don't even have to check it. It has to be. What else? Do we know anything else?
And if it's differentiable, it's continuous.
Has to be continuous. If it's differentiable, it also has to be continuous. Okay, so we might need that, we might not. So I'm going to write that down. Also continuous because of this guy. If it's differentiable, it has to be continuous. Doesn't work the other way though. If it's continuous and not necessarily differentiable. Okay? So this one's similar to the ones we did before. So let's start with differentiable. So let me rewrite it. Actually, you know what? I'm going to write it. Yeah, let me write it over here. F prime of x. A and b are numbers. They're not variables, so don't treat them as variables. So what would be the derivative of the top?
3a.
Just 3a, yeah. Just 3a. For x is less than or equal to -2. The bottom, I have to multiply 2 by 2 and subtract a power. So the derivative would be 4bx minus 1. Okay. I know it's differentiable and I know it's continuous. So I'm going to use those rules to solve for a and b. Because it's not asking you, is it differentiable or continuous? We already know that. We just have to use those rules to figure out what a and b are. Okay, so since we used continuity first the last time, let's do continuity first. Continuous. We know it's continuous, so we're not checking, but we need it to be able to figure out a and b. So the limit as x approaches -2 from the left has to be equal to the limit that x equals -2 from the right, which is equal to f of -2. All of those are going to be the same number. They have to be the same number. So to figure out the continuity from the left, I'm going to use the top. Where do I plug in -2 to the top?
X.
Just for x, not for a, not for b. So it's going to be 3 times a times -2 plus 3. So -6a plus 3. Same thing for the bottom. I'm only going to plug it in for x.
Mr. Flores,
Uh-huh.
can there be several answers to this question? Or no?
I think there's only one. We'll check. Yeah, I'm not sure yet, but yeah, we'll check it out. -2, so you get 2 times b times -2 squared minus a -2 minus 3. -2 squared is 4 times the 2 in front makes 8b. The double negatives make a +2 minus 3, so that's -1. 8b minus 1. Okay. To figure out f of -2, I'd get the same answer as the first one. So it's -6a plus 3. Okay, so I'm going to write that down here. -6a plus 3 has to be equal to 8b minus 1. That has to be true. Now differentiability. Okay, so f prime of negative 2 from the left has to be equal to f prime of negative 2 from the right, which has to be equal to f prime of negative 2. We know that's going to be true because they told us. So if I were to plug in negative 2 to the top, I get negative 6. Nope, sorry, negative 3. Now I get negative 3, or positive 3a. Because there's nowhere to plug it into the top, negative 2. There's nowhere to plug it in because it's x, not a. Plug it into the bottom, there is somewhere to plug it into the bottom. It's 4 times b times negative 2 minus 1. So negative 8b minus 1. And then the last one would be 3a.
Wouldn't negative 2 plus negative 1 be negative 3?
Say again?
Wouldn't negative 2 plus negative 1 be negative 3?
We got to multiply before we subtract because that's minus, right?
Oh, okay.
So we have multiply and then we subtract it. Okay? So we've done this before. We've done this before with continuity where we're trying to solve for a and b. So I have two statements that are true. Negative 6a plus 3 has to be equal to 8b minus 1. Has to be. And I know that 3a has to be equal to negative 8b minus 1. How do I solve for a and b? We're going to use elimination, which we did last chapter. Okay, so elimination. So let me move these guys down. Okay. First thing I'm going to do is get a and b on the same side. I'm going to get a and b on the same side.
Anyone here that's just a...
Okay, so I'm going to get a and b on the same side. So I'm going to subtract 8b from both sides. So I have negative 6a minus 8b plus 3 equals negative 1. And then get everything without an a and a b on the other side. So I have negative 6a minus 8b equals negative 4. Over here, I'm just going to add 8b to both sides. So I have, 3a plus 8b equals negative 1. Okay. Now I'm going to stack them. Negative 6a minus 8b equals negative 4. And 3a plus 8b equals negative 1. Elimination says you want one letter to eliminate. So if I were to add straight down, would one of my letters eliminate, A or B?
Yeah.
B would, right? Okay, so I don't have to do anything. So add straight down. So I get negative 3a, b's go away, equals negative 5. Solve for A. A is positive 5/3, sorry. A is positive 5/3. Which example is it? Example 3. What's up?
Oh, I was going to say, why'd you divide by negative 3, but then I realized that these being multiplied by negative 3.
Oh, okay, gotcha. Okay. Now, solve for b. Well, to solve for b, I'm going to plug it in back into this guy over here. Or you can plug it into this guy over here, or you can plug it into this guy over here, or you can plug it into this. Any of those guys you can plug it into, because I already know what A is, and solve for B. So you know what, I'll plug it in and check. I'll change my mind. I plug it into this guy here. So 3 times A plus 8 times B equals -1. I know what A is, 5/3. So multiply, I get 15 over 3. 15 over 3 is 5. Solve for B. So I get B is -3/4. B is -3/4. This whole step process, we did it last chapter. The only difference is we didn't use differentiability because we had no idea what a derivative was. So this part right here, this part, you've done before. And you did half of this. You just didn't do the differentiable part. Okay? So these types of questions for differentiability are free response questions waiting to happen. You always see this with free response. So free response question is where they'll check, just like last chapter when they check continuity, you guys had free response questions with continuity. You're going to have free response question, at least one with differentiability, guaranteed. That's where they like to ask these questions. Okay? All right. Okay, so now what I want you to do is I want you to try number 4. Same question, different problem, different f of x. Okay? So I want you to try number 4, see what you get for A and B. Okay. So continuity, got 5a minus 6 equals 50b minus 20. Differentiability, I just got a equals -20b plus 3. Okay. This one, -5a, let's see, negative, yep, you're right. Should be negative. Because when I plug it in, it's -5 times a, which is -5a. Okay? So this one you can use, I'm going to show you another method besides elimination. It's called substitution. You can do elimination, it would absolutely work. But this one I think is set up for substitution because I know what A is. That. So what I'm going to do is I'm going to plug that in for A over here. And solve it that way. You can do it that way. Or you can do elimination, you'll get the same answer. So -5, instead of A, I'm going to write what A is, -20b plus 3. Everything else stays the same. $100b minus 15 equals 50b minus 20. Now solve for B.
Oh, you forgot the -6.
-6. I did, you're right. Forgot that too, jeez. Let's see. -6, so I get 100. B minus 21 equals 50. B minus 20. Get the B's on the same side. Get the everything without a B on the same side. I get 50b minus 21 equals -20. should have done it in one step. And then add 21 to both sides. So I get 50b equals 1. Divide by 50. B is 1/50th. Okay, if you know it's 1/50th, you just plug it in. I'm going to plug it in to this guy here. So we get negative 20 over 50 plus 3. Negative 20 over 50 is just 2/5. So it's negative 2/5 plus 3. So what is that, 13/3? 13/5? Because 3 is 15/5 minus 2 is 13/5. Yeah, 13/5. The hardest part about these problems is the math, is the bottom part. And that's math. This guy, you guys did this in Math 1. So whenever you guys took Math 1 in elementary or in junior high or in freshman year, that's just Math 1 stuff. You guys can do that again. It's not hard. Substitution, elimination, that's exactly what they're doing right now in Math 1. So you guys can do it. That's where I see the most mistakes. Okay, it's not so much the calculus. Calculus, we were done up here. Okay? All right, so we'll finish. The rest, there's just some practice problems. The rest are practice. The next one we're going to do has a log in it, but it's exactly the same thing. It just has a log in it. Okay? All right.